Hi and welcome to this junior cycle higher level video where we're going to look at perimeter, area and volume, and specifically looking at circles and the 3D shapes associated with circles, which are cylinders and spheres. So we're going to revise the formula for circumference of a circle, area of a circle, area and perimeter of sectors and arcs, volume of cylinder, we're going to look at the net of a cylinder, surface area of a cylinder, volume of a sphere, surface area of a sphere, and then we're going to explore working backwards. I'm also going to put some exam style questions throughout the video to demonstrate how these could be asked at higher level. So let's start with labeling the parts of the circle. So I have a circle here and I have given you the names of each of the pieces below. So if you want to pause the video and take a second to see, can you fill in the parts of the circle? So the first thing we have is the outside of the circle is called the circumference. The next is the distance from the center of the circle to the outside or to the touching of the circle is called the radius. The diameter is a line that goes directly across the circle through the center. The length of the diameter is always twice that of the radius. We then have a chord. A chord is any line that cuts the circle. We have the diameter is actually a special chord that goes through the center of the circle. We have a tangent, and a tangent is a line that touches the circle once. So it doesn't go through the circle like a chord, it simply touches it on the outside. We then have part of the outside of the circle, and that is called an arc. So it's part of the circumference of a circle. We then have sector, which is like a slice of pizza, and then a segment is a piece of the circle cut off by a chord. These two are often confused, but we'll see how for the sector we have formulas and it is in the log tables, but for a segment there's nothing we really work with at junior cert higher level. So let's look at our first formula. So have your log tables open as we're working through this. My first formula is from page 8 and it's for a circle or a disc. So we're talking about a 2D object. There are two formulas here. The first one is L. L, it tells us there on the right, is length or circumference. So that is the outside of the circle. And the formula is 2 pi r. We then have A. A stands for area, so the area of a circle is pi r squared. Both of those cases, r is the radius. So let's look at a quick example, calculating the area and the circumference of a circle. So find the area and the circumference of the circle below in terms of pi. So what that means is we're going to leave pi in our answer. Notice how the question didn't tell us to use a certain value for pi. In that case, we're using the pi button on our calculators. So let's start with area. So the first thing we're going to do is we're going to write down our formula. That's in the log tables and I have it up here beside us. So we're using A is equal to pi r squared. So my area is pi. I don't sub in for that because they want it in terms of pi. And my radius is 5. So it's 5 squared. Typing that into the calculator, my calculator gives me 25 pi. And because this started in centimeters, the area is going to be in centimeters squared. And that's our answer. They did want this in correct 2 decimal places or 1 decimal place or whole number. We have the S to D button on our Casio calculator or the change button on our Sharp calculator. If your calculator is not defaulting to giving you pi straight away, you may be in the incorrect mode. So it might be a good idea to clear your calculator. You can Google how to do that. You can look up videos on YouTube. So just clear it so that it's in the correct mode. The second part asks us for the circumference. The formula of the circumference is L is equal to 2 pi r. So I'm looking up here. And we're going to sub in. So L is equal to 2. I'm not subbing in for pi, and then r is 5. Putting that into my calculator, I get 10 pi, and length is measured in centimeters. So let's look at example 2. in this case, it's telling us to take pi as 3.14. So we're not using the pi button on our calculator anymore. We're subbing in what they are telling us to use. So a very simple rule to follow when you're doing any exam questions is do what you're told. So in this case, we're told to use pi as 3.14. So if we use pi on our calculator, we're not going to get full marks. So let's start with area. So our area formula is A equals pi r squared. Now we have a little trick here because although I've been told pi is 3.14 and that's fine, my radius is actually not given. In this diagram, they've actually given us the diameter. The diameter is 18 centimeters, meaning the radius is going to be half of that, which is 9 centimeters. Now this is very straightforward to do, but in an exam question, it's very easy to maybe not pay full attention. You're thinking about other things, you're rushing, and you just sub in whatever number you see. So just be really mindful of that. So we sub into our formula, or is 9. So into the calculator, we type 3.14 times 9 squared. And it didn't tell us to do any rounding, so we're going to give the number exactly as we have it, which is 254.34. Area is in centimeters squared. So the second part asks us for the circumference. So L is 2 pi r. We sub in what we have, that is 2 times 3.14 times the radius, which is 9, and putting that into our calculator. Again, they didn't tell us to do any rounding, so we'll leave it exactly as it is. 55.8, and length is measured in centimeters. So it's a good habit to get into when you're working with questions like this, that you write down your formula, you show your substitution, and then you do your calculation. Make sure you're always putting in your units. Sometimes we will be penalised if we do not have our units in. Sometimes we're not, but it's hard to judge when that will and will not happen. So my advice is get in the habit of always putting in your units, no matter what you're doing, and then you'll never lose out on marks. So how do we work backwards? This example is a true higher level style question because we're being asked to not just plug into a formula and use our calculator, which is very straightforward and the kind of thing that we see often at ordinary level, but instead we want to work backwards to find a missing piece of information. So they told us that the area of the circle below is 121 pi centimeters squared. Find the length of its radius. So we're going to start this question in the same way we started our previous ones. We're told area, so in this question I'm only dealing with my area formula, and I fill in area is equal to pi r squared. I fill in what I know. Now this is where it's a little bit different because I actually know my area, so I'm going to plug in area here. I'm not going to sub in for pi, and I don't know my r, so that stays as pi r squared. There is no need to put the centimeters squared into our equation. It's just going to complicate things, so leave that out. We do care about our units, but we care about them at the end. So what I have here is a little equation. It can be really difficult to work with equations, especially when they have a pi. So one thing you can do is really highlight the number or the letter that you want. So I'm going to use green. And I'm going to show my r squared. So I'm trying to figure out that r. You could use a highlighter to do that as well. And there's a pi on both sides, so we can divide both sides by pi. That will simplify our question hugely because the pi dividing both sides mean I'm left with 121 is equal to r squared. Now this is a relatively straightforward question. I like my letter on the left hand side, so I'm actually going to flip my equation. So I'm going to say that, well, if 121 is equal to r squared must be equal to 121. Think back to how we undo a square. To get r, we're going to do the square root of 121, which leaves us r is equal to 11 centimeters. So this is relatively straightforward as a question, but the trick is really setting it up as an equation. It can be hard to remember all the rules and what you need to do. While if you were in the habit of always writing down your formula and subbing in what we have, you'll actually automatically make the equation without thinking too much about it. We're going to see this method again and again as we start working backwards with all of our different formulas in this video. So let's take another example of working backwards. But the difference is here, we're not going to be given our answer, our area, in terms of pi. So we're told the area of a circle is 154 centimeters, taking pi is 22/7, find the length of the radius. So this time we have to sub in for pi. Again, we start with our area. We have area is equal to pi r squared. We fill in what we know. Our area is 154, pi is 22/7, and then we have r squared. So this is a bit trickier because it has a fraction. So the first thing I'm going to do is I'm going to multiply over on this side. I'm going to put r squared over 1. So to multiply, I'm going to multiply across the top. So 22r squared all over 7. So that's just going to clean that up. Now I want to get rid of my fraction. So to get rid of my fraction, I'm going to multiply by the denominator. If I do it to one side, I have to do it to the other side. This 7 divides into the 7 and gives me 1. And now I have balanced my equation, so I haven't really changed anything, but I've got rid of the fraction, which makes life a little bit easier. There are other ways to do it, but I think this is the most straightforward. So we have 22r squared. Now, remember, I'm looking for r, so I'm just going to change the color so you can really clearly see what we're looking for. I like my letter on the left, so I am actually going to flip this around, and I'm going to say, well, 22r squared is equal to 1078. The biggest mistake that happens here is students see the square and say, right, I'm going to square root. But actually, you can't square root yet. You can only square root when the letter is squared, but there's nothing in front of it. There is no coefficient. It has to be on its own. So the first thing we're actually going to do here is we're going to divide across by 22. So by dividing across by the 22 first, it's going to leave me with r squared. And what that gives us is r squared equals 49, and now I can square root it. One thing to remember here is if we were to get a square root of a number that isn't a perfect square, so 49 is a perfect square because 7 sevens are 49. But if we were to get the square root of, say, 90, for example, that is an irrational number. That means that when you put it into your calculator and you press S to D, you'll get decimal places that go on forever. Now, obviously, the calculator cuts it, but in theory, it goes on forever. So what we would need to be told in that kind of question would be how to round it or whether to leave it in third form. So if you have a question like this that doesn't comment on how to round your answer, chances are your answer doesn't need to be rounded. So be very mindful here that you always do that division by the coefficient first, and then we do any rooting that needs to happen. So let's look how this could be asked in a higher level question. So this is from the Junior Certificate Higher Level paper. It's the 2019 paper 2. And the first part of the question asks us to work out the circumference of a circle with diameter 8. So be very careful. In an exam situation, you're under pressure, you're seeing circle, but it's very common for students just take the wrong formula. So make sure you're double checking before you write down formulas that you are looking at the right thing. So we're being asked for circumference, so this is our formula here. So L is equal to 2 pi r. Or is the radius. We haven't been given the radius, instead we've been given the diameter, but our radius is half the diameter. So again, a second little piece that might just trip you up. They didn't tell us what to use for pi, so that means we're using the pi button on our calculator. We go to our calculator and we type this in, we get 8 pi. But the question told us to give our answer correct to one decimal place. So what we want to do is, if you're using your Casio, you're using S to D to change that to a decimal. If you're using Sharp, you are using your change button. So we get 25.1 centimeters. The rubber track for a toy digger goes around 4 circular wheels of diameter 8 centimeters. Notice how this links back to part A. So the work we've done in part A is going to link through to the next two parts. So we can see here in the diagram, we have 4 wheels and a rubber track goes around them. Calculate the length of rubber track that goes around the 4 wheels. Basically what we're being asked is, what's the length of that thick black line in the diagram? So let's break this down. The piece is made up of a semicircle here, a semicircle here, and then we have two straight parts here. So let's have a think how we would do this. So we have a semicircle and a semicircle. And I know it's a semicircle because you can see that we can draw our line, our diameter right here, and that's the curved piece. So the two semicircles make together a circle, and that circle has a diameter of 8. So we're back to part A. So from part A, we've already worked out that the two yellow pieces will have a length equal to 25.1 centimeters. So actually, all we had to do there was think. We didn't actually have to do any calculations. So sorry, I was trying to do my yellow here to show that that's my yellow. Okay. Then we want to see, well, what about these green pieces? So let's go back to our diagram. We have 4 here because it's a radius. We have another 4 here because it's a radius. 4 here, 4 here, 4 here, and 4 here. So we have 1, 2, 3, 4, 5, 6 4s. So that means I have 24 here and 24 there. So that means the total length for the rubber track is going to be the two semicircles, which add 25.1, plus the straight part, which is 24, plus another straight part, which is 24. So we're going to end up with a total of 73.1 centimeters, which is correct to 1 decimal place. Every time the wheel turns fully, the digger travels a distance equal to 1 wheel circumference. So what they're saying here is we will move, if you can imagine, as the circle turns, the length of the outside of the circle, that's how far we will travel. Work out how many times each wheel turns fully when the digger travels a distance equal to the length of its rubber track. So there's a little bit to kind of make sense of here. So if you're kind of struggling to understand it, that's okay. So this is the length of the rubber, and the length of the rubber is 73.1. The circumference of the wheel is 25.1. So how many times will it turn fully? Well, it turns fully every 25.1 centimeters. So we're really seeing how many 25.1s are in 73.1. So what we're going to do is we're going to do 73.1 and divide that by 25.1. So how many full rotations exist when it travels 73.1? And when we do that, we end up with not so nice decimal, but we get 2.91 . But they said how many times will it turn fully? So it actually only turns twice. Now you might go, should I not round that up to 3? But the thing is, it doesn't do 3 full rotations. It only does 2. So what we have here, it will turn fully twice. So each wheel will turn twice when it travels a distance equal to the length of its rubber track. Now let's explore arcs and sectors. So remember from the start of this video, an arc is a part of the outside of the circle. It's part of the circumference. And a sector is a slice of the circle. And it's a very specific slice. Think of like your piece of pizza. It is a slice that is made from 2 radii. So basically we're cutting to the center. We have this formula here on page 9 of our log tables. We can see the shaded piece. So that is what we think of as a sector. The sector has an angle, and that angle is called theta. Now, theta is just an angle letter that we tend to use. It is a Greek letter that looks like this when I draw it. It is theta. It's the same as if you called it A. It's just another letter. When we run out of letters, we tend to use our Greek letters in maths. We have our radii, we have one here, but also one here. And then we have L, which is the length of the outside. So if we're talking about the length of an arc, we're talking about this piece here. The 2 pieces of information that we want to find out are L, the length of the arc, so how long it is, and A, the area of the sector. So just to be aware of both of those terms, so we tend to get L, the length of the arc, and A, the area of the sector. Now we can do other things with sectors, and we'll talk about that as we do the questions. How we work this out is using our formula. If you're looking at page 9, you'll notice that there is another line, and that has the theta is in radians. This is not something we look at Junior Cert. We focus on theta in degrees. So our formula for L is equal to 2 pi r, which is our original formula for the length of the circumference. And then we have this little piece here, which is theta over 360. Now, all this actually does is it gets a fraction. What fraction of the circle are we working with? So imagine that theta is 90 degrees, so 90 over 360. So if you have your calculator handy, put that into your calculator. 90 over 360, and you'll get a quarter. So what you will do is you'll get your length of your circumference of the whole circle and then find a quarter of it, because you're dealing with a quarter of the circle. So the formula is one that you can use directly from the log tables, but some students actually prefer to find the fraction themselves and work that way. For the area formula, something similar happens. Area is pi r squared, which is the area of the circle. And again, we find, well, what fraction of the circle are we actually working with? So again, if I had 90 degrees, 90 over 360 gives me a quarter. So I'm getting a quarter. If you were dealing with a semicircle, and semicircle is actually a sector, this will be 180 over 360, which will give you a half. So if you feel more comfortable not using this formula, if you feel more comfortable finding the fraction yourself and multiplying that by your original formula, that's fine. That's all the formula is doing anyway. So let's take a look at an example. So find the area of the following sector. Leave your answer in terms of pi. We can see here we have a sector, a piece of the circle. So our formula for the area of a sector is A is equal to pi r squared, and then we have theta over 360. So let's fill in what we know. The area is, and now notice how they asked us to leave our answer in terms of pi. So when we sub in, we're not subbing in for pi. Our radius is 28, so that is 28 squared. And then the angle is 120 over 360. Now, you don't need to simplify it. You can go straight to your calculator and put in the whole thing. But if you want to just check this out, 120 over 360, let's just put a little arrow there. So 120 over 360, we're dealing with a third. So this sector is 1/3 of the circle. So what we're saying is let's get the area of the full circle and then find what is a third of it. So if you're going into your calculator, you can do pi 28 squared and just use your brackets. You can use a multiply sign if you find that easier. And the answer that this spits out is 784 over 3 pi, and then we have centimeters squared for our area. So it's a nice straightforward little formula. If you wanted to work it using the area of a circle, so pi r squared, that would be pi by 28 squared. That gives us 784 pi. I'm not using my full circle. I only have a third of a circle. So what I would do is I'd get, so my area of the sector is going to be 1/3 of 784 pi. And we end up with exactly the same answer. So 784 3 pi centimeters squared. So if you prefer, if this is the way you've learned how to do it, that is absolutely fine. I like the formulas because you've less thinking to do in an exam situation. So example 6 is, let's find the perimeter of a sector. So find the length of the arc and hence the perimeter of the following sector. So remember when we were looking at our log tables, I said that this L is length of the arc. So what that means is it is specifically just looking at that curved piece here. So it's the bit of the outside. Now this question asks us for that, but then goes on to ask us, well, what is the whole perimeter of the sector? Now the perimeter of the sector includes 2 radii. So we also have this section here and this section here that makes up the outside. Now both of those are straight lines and they're both a radii. So we have 14 centimeters here as well. So if you're just asked perimeter, just make sure that you're adding in those two lengths as well. So let's start first with the length of the arc. So we have, let's do it in red. L is equal to 2 pi r theta over 360. Again, if you want to do this using the idea of just 2 pi r and then find a fraction, that's perfect. They did not tell me what to use for pi, so I'm putting in pi as is. My radius is 14. The angle is 45 over 360. The difference is here, they want our answer correct to 1 decimal place. So even though we'll have an answer given to us in terms of pi, we're going to press either our S to D or our change button to figure out what our answer will be correct to 1 decimal place. So the length of my arc is this, 7 over 2 pi. I'm going to change that. I get 10.99557 which actually rounds up to 11.0 as decimal places. So that's centimeters. The perimeter is going to be 14 plus 14 plus my 11.0, which is 39.0. They asked for 1 decimal place, so I'm going to leave that 0.0 in there, and that is my perimeters. Just be very mindful when you're doing a question. If they had simply asked us for perimeter, then we wouldn't have to worry about the idea of the length. I wouldn't have had to round it fully. I could have rounded this all at the end. I wouldn't have had to put in my units. But here they asked me to find the length, which is kind of the first question, and then hence the perimeter. So there was 2 parts to the question. So I need to make sure I have both my answers here. With regards having those answers, I mean, I have to have them rounded correctly and I have to have my units in place as well. So just be careful. Is it part of the question? Is it something that you need? If so, make sure you have your units, make sure you have rounded correctly. So let's look at the area of a compound shape. So here I have a compound shape, I have a semicircle and I have a rectangle, and it asks me to find the area of the shape taking pi as 3.14. So compound shape is a shape made up of other shapes. If you haven't already revised area and volume of triangles, I've linked the video in the description below. We meet kind of our compound shapes there in more detail. So let's break this up. I am a little bit lazy, so I like to draw rather than use words to label. So let's start with our semicircle. So our semicircle is actually a sector. It is a sector that has an angle of 180 degrees here. And I'm going to use that fact. If you want, you can just take the circle and divide it in 2. That's perfect as well. So my area of this, I'm going to use my sector formula. So pi r squared times theta over 360. I have pi, they did tell me 3.14. Now the radius is not obvious here. So take a look. We have a rectangle. So our rectangle is here. A rectangle by definition, opposite angles are equal. Opposite sides are equal, so this side must equal this side. So we end up with 16 here. And for our semicircle, that would be a diameter, meaning that the radius would have to be half of that, meaning my radius is going to be 8. So let's put that in here. So that's my 8. And I put 8 squared in here. I then have 180 over 360, or you can just simply go straight to multiplying that by a half. So we put that into our calculator, 3.14 by 8 squared by 180 over 360. They didn't tell me anything to do with regards rounding, so I'm going to give it exactly as it is. So I get 100.48. This is area, so it's centimeters squared. So that is the semicircle piece. We then also have a rectangular piece. So the area of a rectangle is length by width. It doesn't matter which is which. Remember, multiplication is commutative. Order will not matter. So all you need to do is multiply your 16 by your 9 or your 9 by your 16. And that will give us our area of that piece. That gives me 144 centimeters squared. So then the total area is just going to be a combination of my two shapes. So that's going to be 100.48 plus 144, and we end up with 244.48 centimeters squared. So that is the area of the compound shape. So just to remind yourself that actually semicircles, they are sectors, so you can use your sector formulas from your log tables to help you with those. And so this is from the Junior Certificate Higher Level 2018 paper. A pizzeria has the following poster: 9-inch pizza special offer. Note, 9-inch pizza is equal to 2 slices of big pizza. So a 9-inch pizza in the shape of a circle with diameter 9 inches, and each big pizza is in the shape of a bigger circle and divided into 6 slices of equal area. Use the information on the poster to work out the radius of the big pizza. Give your answer in inches in the form 3 to the power of p over 2, where p is an element of q. So there's a huge amount going on in this question. The first thing we're going to do is try draw out what's happening. So a 9-inch pizza is in the shape of a circle with diameter 9 inches. So here is my pizza. It has 9 inches across. That's its diameter, which means its radius is 4.5 inches. Okay, then a big pizza is going to be a bigger circle divided into 6 equal slices. Now, what we're told is the 9-inch pizza, so this one here, I'm going to color it in, this is the same as 2 slices of big pizza. So let's have our 2 slices here. So these are equal. And what I mean by equal is the area of both pieces is the same. So what we're dealing with on the left is a circle. What we're dealing with on the right is a sector. So in terms of the sector, we have a full circle, 360 degrees, divided into 6 equal pieces, which means each of these sectors has an angle of 60 degrees. So the sector that we're looking at is going to be this piece here, and that has an angle of 120 degrees in total. So we know that the area of the circular 9-inch pizza is going to be equal to the area of the sector. So let's get the area of each piece. So the area of the circle is pi r squared. So this is pi times 4.5 squared. Now, when you put that into the calculator, you get 81 over 4 pi. And we're going to leave this in terms of pi. The reason we're going to leave it in terms of pi is if you try to use decimal, you're going to end up rounding it, which is going to lead to our answer being a little bit inaccurate. So then we're going to do the area of the sector over here. So that's pi r squared theta over 360. So that area is going to be pi times r squared. That's what we're looking for. And that's 120 over 360. Now 120 over 360 simplifies to a third. So that's pi r squared and a third. So because these two pizzas, the pizza on the left and the 2 slices on the right, because they're equal, we can say that 81 over 4 pi is the same as pi r squared times a third. Now, the first thing I'm going to do is I'm going to divide both sides by pi, which gets rid of the pi. So that makes life a little bit easier. I then am left with 81 over 4 is equal to, let's multiply this across. So I have 2 fractions, I'll put r squared over 1, multiply across the top, r squared times 1 is r squared, over the bottom 1 by 3 is 3. I now have two fractions. I want to get rid of them, so I'm going to multiply by the lowest common denominator. The lowest common denominator of 4 and 3 is 12. 3 goes into 12 4 times, 4 goes into 12 3 times. So we get 3 times 81, which is 243, and that is equal to 4 or squared. We're trying to figure out what or is. So I'm going to flip this around because I like my variable on the left hand side. So instead of having 243 is equal to 4 or squared, I'm going to have 4 or squared is equal to 243. I'm going to divide both sides by the coefficient, which is 4, and that's going to leave us with or squared equals. Now the thing is, this does not simplify. It stays exactly as it is. We're going to now get rid of the square, and we do that by square rooting. So or is equal to the square root of 243 over 4. And when you put that into your calculator, you're going to press the square root button and then use your fraction button underneath, and you end up with 9 root 3 over 2. And that will be in centimeters. Now the problem is that's not going to get you full marks. It's not 100% correct because they want this in the form 3 to the power of p over 2, where p is an element of q. And what that means is p is a rational number, so it'll be a fraction of sorts. The bottom line is good. We've got that bottom line of 2, but the top line needs a little bit of work. We're now going to work with our rules of indices, which are on page 22. Now, if you've not already covered your rules of indices, you've done pretty much as you can, but what you're aiming for the final exam is to be able to complete all of these questions and the mix of topics within the questions. So what we're going to do now is we're going to take this 9 root 3 and we're going to work with that a little bit with our rules of indices to make it a 3 to a power. So let's focus on that top line. So I have a 9 root 3 and I want to write this as 3 to the power of p. Remember that 2 on the bottom, we're good. That's no issue. So let's break all of our pieces down to 3 to a power. So 9 is 3 squared. And using our rules of indices on page 22, the square root of 3 is going to be 3 to the power of 1 over q. So the number that should be here that we don't write there is a 2. So this is 3 to the power of a half. So this is going to be 3 to the power of p. So when I want to multiply two numbers where it's the same base, I'm going to use my law 1 here, which tells me to add my power. So that's 2 plus a half. And then 2 plus a half, you can do that in your calculator. You get 2 and a half, or 5 over 2. That means that p is equal to 5 over 2. So our final answer is going to be or equals 3 to the power of 5 over 2 all over 2. And this is in centimeters. Oh, apologies. This is in inches. So when we're working with a question like that last piece, don't let that deter you from doing the rest of the question. The bulk of this question is an area working with the circle, working with the sectors, and the only thing that we were missing was that last bit of indices at the end. So now let's take a look at a 3D shape that is related to the circle, and that is a cylinder. So a cylinder is, if you can imagine, a lot of little circles piled on top of each other, and they're all identical, piled on top of each other to create this lovely three-dimensional shape. A cylinder has two dimensions. It has a height and it has a radius. So the area here in our log tables, A, is the curved surface area, and we're going to talk about that in a little bit more detail because this is an important one. And the formula is 2 pi or h, And then V is for volume, and that is pi r squared h, and that is very straightforward to work with. So let's take an example of calculating the volume of a cylinder. So a candle in the shape of a cylinder is put into a box. The candle has a height of 4 and a radius of 1.2. Find the volume of the candle correct to the nearest centimeter cube. So when we deal with volume, we're talking about centimeters cubed. So our volume formula is pi r squared h. They didn't tell us what to use for pi, which means we're using the pi button on our calculator. Or is 1.2 squared, and our height is 4. We go to our calculator. We're going to type this in. It will give it back to us in terms of pi first. So we get 144 over 25 pi. We're then going to change that to be 18.095573 ... And we want that to the nearest centimeter cube. So we're cutting it here. The next number is 0, so it's staying as it is, which means my volume is going to be 18 centimeters cubed. So I pulled up the whole page here from our log tables. This is page 10, so we can explore the idea of the surface area in a little bit more detail. So surface area is the outside of the shape. Notice how for the cylinder we have A equals 2 pi over h, and up the top here it says in the following, A represents the curved surface area, and that's really important. So A represents the curved surface area. So what we mean by curved, it's the bit that physically is curved, it's not flat. So we're talking about this part here. Why this is important is because in a question, they may just ask you for the surface area or total surface area. And in that case, it will include the top and the bottom of the cylinder as well. So it's really important to remember that when we use this formula is only finding the piece, the curved piece, the piece around. Think of your Pringles can. It's the bit that your hand goes around, your can of Coke. It's the bit your hand will hold. So let's take a tin of baked beans and specifically the label, because the label will help me demonstrate this a little bit better. So where does that surface area formula come from? So when we deal with that curved piece, we really need to take into account the circumference of the top circle. So the circumference up at the top is the bit that goes around the whole cylinder. So if we can remember back from the circle, the circumference of a circle is 2 pi r. So if I were to open out that label, I end up with a rectangle shape like this, and it has a height h, but it has a width equal to the circumference because it needs to wrap around that whole top circle. So if I were to find the area of that rectangle, it will be the width 2 pi r by the height, or the width or the length, whatever you want to call them. So 2 pi r by h, and that gives us that curved surface area formula. So if you think it's a bit funny, just remember we're trying to wrap that rectangle around the circle, so we link it back to circumference. So sometimes we're asked about the nets of shape. We met nets in more detail again in the area and volume video on triangles. That's linked in the description below. But for a cylinder, this is what it looks like. We have that rectangular piece that creates the kind of curved part, and then we have two circles, one at the top and one at the bottom. So a challenge is often to try and create a 3D model of a cylinder, and it's a question I like to give to my classes at a lot of different levels, because until you go to build it, it's very easy to dismiss the link between the circle and the rectangle, and that's one of the biggest issues that students have. It's forgetting, or I suppose not remembering, that that rectangle has to wrap around the circle. So it's not the rectangle can be any size at all. It has to be a very specific width, and that width must be equal to the circumference of the circle. So it's a good challenge. Pick a cylinder from maybe the video or from your book and see, can you create first of all the net, and then cut the net out and see, does it create the cylinder with the correct dimensions. So So let's take a question where it's asking us to find the total surface area of a cylinder. So we have a cylinder here. They're telling us to use pi as 3.14. And in this cylinder, we have two dimensions given to us. They give us the height, and then they also are giving us the diameter. So this is, the diameter is 28, meaning the radius is going to be 14. So the first thing I'm going to do is I'm going to get the curved surface area. Now I call this CSA for short. And that area is 2 pi or h. My area is 2 by, the pi is 3.14 in this question, the radius is 14, and the height is 30. They didn't say anything about rounding, which means we're going to leave our answer as is, and when we do that, we're going to get 2,637.6 centimeters, and because we're dealing with area, it's squared. Just be careful. Sometimes students think, oh, we're dealing with a 3D object, everything is power 3. It really depends what you're calculating. Because the area can be flattened into a two-dimensional shape, it is still centimeters squared. As well as the curved piece. So effectively what we've worked out for the curved piece is the rectangular piece in the middle. We also have a top and a bottom. So we have two circles here. Now the circle areas are going to be pi r squared and pi r squared. They're identical. So what you can do is you can do it once and then double your answer. So that gives us area is equal to 3.14, and the radius is the same as the radius of the cylinder. So that is 14. So 3.14 by 14 gives us 43.96, and then I have the top, which is 43.96, and I have the bottom, which is 43.96. And then what I need to calculate is, I say TSA for short, the total surface area, 2,637.6 plus 43.96 plus 43.96. And when you add all those together, we end up with 2,725.52 centimeters squared. So just be very mindful. Are they asking me for the total surface area? Do I need to do more than just the formula? Or are they just asking me for the curved surface area? When we deal with cylinders, cylinders can be something solid and closed. They can be open on one end. So go back to maybe our tin of Pringles for a second. When I have my lid on top and it has a base, in that case, the total surface area would have a top and a bottom and the curved surface area. If I were to lose the lid and use it for something else, so for example, it's open at the top and closed at the bottom, like a glass, in that case, your total surface area would only include a bottom. And in some cases, a cylinder is actually a pipe. So think of something like a straw where it is open on both ends. In that case, it only has a curved piece. So be aware in exam questions, they could change up the type of cylinder we have. It could be a closed cylinder, so closed on both ends. It could be open at the top, so like I said, something like a glass, or it could be open on both ends, which would be like a pipe. So let's work backwards with our cylinder. The volume of a cylinder below is 288 pi centimeters cubed. Find the radius given the height is 8. So if we want to work backwards, we do the exact same thing we would do as if we're working forwards, which is start with our formula. So volume is equal to pi r squared h. The volume in this case is 288 pi. I'm going to leave this in terms of pi because I wasn't told what to use for it. I'm looking for the radius and I have a height of 8. First thing I'm going to do if I have pi's on my question, get rid of my pi's. So divide both sides by pi. I end up with 288 is equal to, be careful here on the right hand side, the or is squared but the 8 isn't, so I end up with 8 or squared. I like my letter on the left, so I'm going to flip this, so 8 or squared is equal to 288. It's important to remember when we're dealing with something like this, you always divide by the coefficient first and then you square it. So we end up with or squared is equal to 36. That kind of makes sense. They didn't ask us to do any rounding, so we are expecting a perfect square there, which 36 is. So we get the square root of 36. Perfect square means that we'll get an answer without decimals for this, and we get 6 centimeters. So remember, the key idea here when we want to work backwards is creating the equation. But rather than remembering it, it's better to get in really good habits. So when you're dealing with any area and volume formulas, you always write the formulas and fill in what you know. That way, it kind of automatically creates the equation without you having to worry too much about it. So let's work backwards for the volume of a cylinder when we're not giving it in terms of pi. So it's 1,848 centimeters cubed. Find the radius given the height is 12 and give your answer correct 2 decimal places. Take pi as 3.14. So again, we start with our volume. Volume equals pi or squared h. We fill in what we know, so we know the volume is 1,848. We know pi is 3.14. We don't know the radius, but we know the height is 12. We do a little bit of cleanup on the right hand side. So remember, multiplication is associative, which basically means if you're multiplying 3 pieces together, it doesn't matter which 2 you do first. So for us, we're going to do the first and the last because they're both numbers. So I get 1,848 is equal to 37, oh, I dropped my squared, 37.68 or squared. I like my letter on the left, so I'm going to bring that across. In this question, they did tell us that we'll need to round, which tells me that my answer is not going to be a perfect square, but I follow the exact same process as we have done before. So first thing I'm going to do is I'm going to divide by the coefficient, so 37.68, divide that on both sides. I'm not going to get a particularly nice answer. I basically end up with or squared equals 49.04458599. I'm going to keep that as accurately as possible. And the way I'm going to do that, rather than try type it out again, because if I type it out again, I'm probably going to make a mistake. I'm going to use my answer button. So or is going to be the square root of this number. So it's going to be pretty close to 7. But what I'm going to do in my calculator, I'm going to press square root and I'm going to use my answer button. And my or is equal to 7.00318 ... and I want 2 decimal places, but actually my 2 decimal places are 0, 0. So it actually works out pretty close to 7. So let's take a look at an exam question, and this one is from the Junior Certificate Higher Level 2014 paper. This was from a sample paper. So Deirdre constructs a polytunnel on a level part of her back garden. 5 vertical semicircular metal hoops, each of radius 2 meters, are attached to brackets at ground level and covered in a polythene sheet. The hoops are 2 meters apart. Find the area of ground covered by the tunnel. So the diagram in part 2 is helpful here. So basically the shape on the ground is a rectangle. Since the radius is 2 meters, the whole length across here is 4 meters. So let's sketch out. So here is the front, so that is 4 meters, and the back is also 4 meters. We're also told that the hoops are 2 meters apart. So this is 2 meters, 2 meters, 2 meters, and 2 meters, meaning this length here will also match it, which means that that is 8 and the other side is 8. So the area is just the area of a rectangle that is 4 by 8, so that is 32 meters squared. So use any diagrams, even if they're later in the question, to help you with what you're being asked. The hoops are also held in place by a straight metal attached at the top of each hoop. Find the total length of metal needed to construct the polytunnel. Okay, so this piece here we know is 8 meters. So we have that straight line and we know that that is 8 meters. But we also have 5 semicircular hoops. We're looking at circumference here. So in our log tables, that is 2 pi r for a whole circle. And then we'll end up dividing that by 2 in order just to get half of it. So we are going to have our L as 2. They gave us no indication what to use for pi, so let's leave it as pi button in our calculator. Our radius is 2, and then we divide that by 2. So we end up with the length of each of those pieces as 2 pi, and then we're going to multiply that by 5, which gives us 10 pi. So then the total length is going to be 8 meters plus 10 pi meters. So let's add those together. So 8 plus 10 pi, and we get 39.41592 ... meters. It didn't tell us what to round to because it was a sample paper, so let's just do 1 decimal place, so 39.4. Part 3 then says the polythene is buried in the ground to a depth of 25 centimeters all around the tunnel, including both ends. Find the dimensions and the area of the smallest rectangular sheet that can be used. So we're going to really want to figure out how do we cover this structure. So we want to find the area of this piece. We also want to find the front and the back. So what we're talking about here is surface area. Now we're talking about surface area of a cylinder, but we're also looking to bury it 25 centimeters deeper around the tunnel and at both ends. So let's try and make sense of what they're asking. So this question is quite tricky. We're being asked to use or to find one sheet that will cover the whole thing. So let's start with the curved piece. So we're talking about covering this section here. So the piece of plastic that will need to cover this section here needs to go around the hoop, meaning it's going to have a width equal to the length of that arc. And we've already worked out that as 2 pi in our previous part. Now, this piece here is going to be equal to 2 plus 2 plus 2 plus 2, which is 8 meters. But it'll also need an additional 25 centimeters at either edge that can be buried in the ground. Now, notice how this is in centimeters. So 25 centimeters is 0.25 meters. So we need to add in an additional 0.5 meters to the width of this section. And it's just that section. So that's the middle bit done and the dimensions of it. But we're going to need to think about the plastic also has to cover each end. So think of our front. It's a semicircle and then has an initial piece here. So we're going to need to add on to that piece of plastic an additional piece here. Now, in my semicircle, this is my radius and it is 2 meters. And then it has that additional 25 centimeters to go below the ground. So this is going to be 2.25 meters on this end. And we're going to do exactly the same up in this end. So this is going to have 2.25 meters as well. So if you can see, I've drawn a larger box around the whole thing, and that represents the piece of plastic that we need. That piece of plastic is going to have a width that is 2 pi plus 0.5 meters. And then this length here is going to be 2.25 plus 8 here plus 2.25. So the dimensions are the length of this. Well, it doesn't matter which one you call length and which one you call width. That's absolutely fine. So the length I'm saying is the down piece. It's 12.5 meters. We then have a width of 2 pi plus 0.5, which is 6.783. And then the area is length by width, which is 12.5 by 6.783, 783, and we get 84.7875. It didn't tell us how to round, but let's go one decimal place. So 84.8 meters squared. So there are our dimensions. So a tricky little question. They weren't asking for the area of the outside in the conventional way we would think about it. Instead, they were looking at that one sheet that will cover the whole thing. So it's a take on our surface area. So the last part of this question is to find the volume of air in the tunnel. This is very straightforward. So what I would say is don't assume that because a part is hard, the rest of the question you won't be able to do. Here we have a very straightforward volume question that we'll be able to do regardless of how we found the previous part. So the volume of the tunnel is going to be the volume of the cylinder, but since it is only half of it, we're going to divide it in two. So this is pi times 2 squared. The height in this case is equal to our 8 here, because we think of it as being on its side. And then you divide by 2. So that gives us 16 pi, and let's go to one decimal place again. And because it's sample paper, it hasn't specified how we should do it, but in an exam they will tell us how to round, and that works out as 3 centimeters cubed. Let's look at another junior certificate higher level question. This one is from the 2013 paper. So the dimension of two solid cylinders are shown in the diagrams below. Calculate the ratio of curved surface area of the smaller cylinder to the curved surface area of the larger cylinder. So there's a few things that make this question tricky. The first is the idea of writing a ratio. That often gets students quite confused as to what we have to do. But don't let that stop you. That's just how we're going to display our answer at the end. We really want to focus on what they're asking, which is the curved surface area of the smaller cylinder and the curved surface area of the larger cylinder. So let's work with that. The second thing that's challenging is the fact that there is actually no numbers. So I'm going to call this the curved surface area of the smaller, and that is 2 pi or h. And then the area of the bigger one is 2 pi or h as well. Now, the difference happens when we sub in. So this is going to be instead of the radius or and instead of the height h. Nothing happens. But over for the bigger cylinder, we have 2 pi. The radius is 2 or and the height is 2h. So what we want to do is we want to multiply all the numbers we can see together. So I see a 2 and a 2 and a 2. So 2 by 2 is 4, by 2 is 8. So this ends up at 8 pi or h. So we now have the two surface areas. And this is just the curved surface area, so that's why I don't have to worry about the top or the bottom. And what they want us to do is write this as a ratio. So simply, we're going to write 2 pi or h is to 8 pi or h. Now, a ratio is in some way related to a fraction, so we can simplify it in a similar way. So because there's a pi on both sides, we can divide both sides by pi. Because there's an or on both sides, we can divide both sides by or. And because there's a h on both sides, we can divide both sides by h. So we get 2 is to 8. That's much easier to deal with. We can divide both sides by 2, and we get 1 is to 4. Part B then asks us to find the volume of the ratio of the volume of the smaller cylinder to the volume of the larger cylinder. So again, let's focus on just getting the volume, VS is going to be pi or squared h, and the same for the big. The difference is going to happen with our substitution. So this is pi or squared h, nothing changes. For the big cylinder, we have pi, the radius is 2r and that's squared, and then the height is 2h. So we must follow our rules of BIMDAS, and BIMDAS tells us we must do any brackets first, do what's in the brackets, and then indices. So let's focus on working with this piece here. So 2r all to be squared actually gives us 4r squared. So both the 2 and the r must be squared times 2h. Focus on the numbers you can see. I can see a 4 and a 2. Let's multiply them. I get 8 pi or squared h. So now let's write our ratio. Our ratio is pi or squared h is to 8 pi or squared h. Let's divide both sides by a pi. Let's divide both sides by r squared and divide both sides by h. Since we're dividing, anything divided by itself leaves us a 1. So we end up with an answer of 1 is to 8. So although this seemed like a very tricky question, don't get thrown off by the lack of numbers. The letters all cancelled out in the end, and don't be thrown off by the idea of ratios. Ratio is just a way to write your answer. So it is using our dots to put one number to another and simplifying like we would in a fraction. Now let's look at the sphere. Now the sphere is specifically for higher level, and it is in our log tables on page 10, and we have two formula. We have an area formula, which is the curved surface area for pi or squared. The thing about spheres is they only have a curved piece. It's all curved. So in order to work with getting the whole surface area, it's the curved surface area. So we don't have to do anything too special with spheres. This will impact us though when we start working with hemispheres. V is for volume. It is 4/3 pi r cubed. Again, just be really mindful when you're going to your log tables to get your formula. I often see students mix up these formulas, which is a terrible way to start your question because you're straight away losing marks for something very silly. So let's look at an example of the volume and surface area of a sphere. So taking pi is 3.14, find the volume and the surface area of the sphere below. Give your answer correct to 1 decimal place. Okay, so the first one is volume. So let's start with our formula. Volume is 4/3 pi r cubed. In this question, they gave us the diameter, and that was 18, so the radius is going to be 9. So this is, the volume is 4/3 times 3.14 times 9 cubed. So make sure you're comfortable with where your cubed button is. So 4/3, 3.14 by 9 cubed, and we end up with 3052.08. They want that correct to 1 decimal place, so we cut it here. Look at our next number. That's 3052.1 centimeters cubed. Our second part is asking for the surface area. So we're going to work, I'll go straight to the formula. With the formula, A is equal to 4 pi r squared. Really be mindful of your powers here. I often again see students use the correct formula, but then they mix up their powers, so just be careful. This is 9 squared, so 4 by 3.14 by 9 by 9, and we end up with a surface area of 1017.36, 1 decimal place, which means the 6 here will round the 3 up, so we get 1017.4, and area is always centimeters squared. So really straightforward to work with these formulas. Don't be put off by the powers or the fraction. The calculator is going to do most of the work. So now let's work with a hemisphere. So here we have half a sphere and we're being asked to take pi as 3.14, find the volume and then the surface area of a hemisphere. Give your answers correct to 1 decimal place. Now we don't have a formula in our log tables, however we can work with this as a sphere and divide it by 2. So for our volume of a sphere will be 4 over 3 pi r cubed, and then we're going to divide our answer by 2. In this case our radius is 7. So we have 4 over 3, pi is 3.14, we have 7 cubed, and then we divide that whole answer by 2. That gives us 718.0133333. 1 decimal place, we're going to cut it here, so that actually leaves us with the volume as 718.0 centimeters cubed. Now, in order to work with the surface area, the A in our log tables, 4 pi r squared, is the curved surface area. Now that doesn't impact us when we're working with the sphere because the sphere is completely curved, so there is no additional area we need to think about it. However, when we cut the sphere, like we have done here with the hemisphere, we end up with half the curved surface area, which is this one here, but we also end up with a flat piece that is here. Now think of cutting an orange. This is a circle with the same radius. So we need to do 2 things here for surface area. We need to get 4 pi r squared, which is the curved piece, divide that by 2, and then that gives us the curved surface area piece. We then have a circle that we need to deal with, and the area for that is just the area of the circle formula, pi r squared, and we're going to add these 2 together. So this curved surface area is 4 times 3.14 times 7 squared, but dividing our answer by 2. For this, we're going to have 3.14, and we have 7 squared. They give us A equals 307.72 plus this one gives us by 7 squared. That gives us 153.86. So adding those together, so 307.72 gives us 461.58, which we need to cut and round. So our total surface area is going to be 461.6 centimeters squared. So just to be aware of that additional piece when we're working with surface area. So the volume of all these shapes are relatively straightforward, but it's the surface area that you need to be a little bit more mindful and really remember that in our log tables, the A for our 3D shape is a curved surface area formula. So let's work backwards with the sphere. So the volume of a sphere is 288 pi centimeters cubed. Find the length of the radius of the sphere. So just like all of the other questions where we worked backwards, let's start with our formula. V is equal to 4 over 3 pi r cubed. Now this is the trickiest one we'll meet because it has a fraction and it also has a power 3. But we approach it in exactly the same way. We start with 288 pi as the volume. 4 over 3, we leave this in terms of pi, we're not subbing in, and then we're looking for that r. First thing I always do is I divide across by pi. That means the pi's disappear and my equation's a little bit easier to work with. I now have 288 is equal to 4 over 3 r cubed. I'm not mad about fractions, so let's get rid of those by multiplying both sides by 3. These 3's, 3 on the top and 3 on the bottom, they divide into each other, leaving us with 1. So we do 3 times 288, which gives us 864 is equal to 4 r cubed. Now, I don't like my letters on the right hand side, I prefer them on the left, so I'm going to flip this equation. In order to find r, I first need to divide across by the coefficient. So I divide by 4 and I end up with r cubed is equal to 216. Now, we're used to working with squares and using our square root to go backwards. For a cube, we have something similar. It's called a cubed root. So it looks like a square root, but it has a little 3 here. So on my calculator, it's above my square root, so I use shift and the square root button. And the question it's asking is, what number multiplied by itself 3 times is going to give me 216. So when you put that into the calculator, you're going to get your answer of 6 centimeters. So some of the things that cause problems with a question like this, the fraction. So get rid of that. If you're not a fan of fractions, get rid of the fraction straight away. And the next thing is making sure that you divide across by the coefficient before you apply any roots, be it square root or cubed root. And again, they didn't ask us to do any rounding in this question, which meant that chances are we're going to get a nice whole answer number, which we did. If that's not happening, something has gone wrong. Maybe you've done things in the wrong order. Double check your work. Let's look at another question working backwards, but this time let's look at surface area. So the surface area of a sphere is 616 centimeters squared. Taking pi is 3.14. Find the length of the radius. So our area formula, really keep a close eye on the formulas that you're using. Make sure you're using the right ones. Take a second. They're there in the log table, so make sure you're not losing marks by pulling the wrong one. So they're telling us to use 3.14 for pi. The radius is what we are looking for. So let's multiply what we can. So in this case, let's multiply 4 by 3.14. And when we do that, we get 12.56. And that's r squared. I like my letters on the left, so I'm going to switch up my equation. And now I'm going to divide by the coefficient. So 12.56. So 6 on 6 divided by 12.56. I get r squared is equal to 49.04458 and so on. In order to be accurate, when we apply the square root, in my calculator, I'm not going to retype this because I'll probably make a mistake, and also I'm a little bit lazy. So instead, I'm going to use square root and the answer button. So in my calculator, I'll write it here. I draw the square root and then use my ANS button and then press my equals. And that gives me 7.00. Just means I don't have to retype a number that was already on my screen. And this works out as 7 centimeters. So I get 7.00, so we can drop those. Now let's look at an exam question. This is from the Junior Certificate Higher Level 2015 paper. And it's about a sphere. So a small sphere has a radius of 1.5 centimeters. That's an important piece of information. Find the volume of the small sphere, giving your answer in centimeters cubed. So nice straightforward our little question first with our formula. So we have 4 over 3 pi r cubed. Let's fill this in. So we get 4 over 3. Didn't tell us what to, oh sorry, it did. It said leave your answer in terms of pi. So pi in our answer, and then 1.5 cubed. So we go to our calculator and we put 4 over 3 multiplied by pi multiplied by 1.5 to the power of 3, and we get 9 over 2 pi centimeters cubed. So the volume of a large sphere is 3 times the volume of the small sphere. So the volume of the large sphere is 3 times. So this is 3 multiplied by the volume of the small sphere, which is 9 over 2 pi. So the volume of the big sphere is going to be 3 times multiplied 9 over 2 pi. So go to our calculators. If your number is already left there, just multiply that by 3 and we end up with 27 over 2 pi, and that's the volume of this new big sphere. It then says, find the radius of the large sphere, giving your answer in this form here. Now again, this can look daunting. It is a working backwards question, but it's going to have a little bit of work with indices. That's at the very end, so let's focus on getting an answer and then we'll look at converting it. So we want to find the radius, so let's go to our volume formula. So volume is 4 over 3 pi r cubed. We've now worked out that the volume is 27 over 2 pi, and that is equal to 4 over 3 pi r cubed. Let's divide both sides by pi to make life a little bit easier straight away. And now what we have are two fractions, so 27 over 2 and 4 over 3 r cubed. So the lowest common denominator of 2 and 3 is 6. So let's multiply both sides by 6. That will get rid of both of our fractions. So 3 in the bottom, 3 in the top, that goes twice, 2 into the bottom and 2 into the top, that goes 3 times. So we have 3 times 27, which is 81, is equal to 2 times 4, 8 r cubed. Now, I'm not mad about having my letters on the right. I prefer them on the left, so I'm going to flip them around. And when I have 8 r cubed equals 81, my next step is to divide by that coefficient. R cubed is equal to 81 over 8. It doesn't simplify. And then we're going to apply our cubed root. So r is equal to the cubed root of 81 over 8. Now, when we put that into the calculator, so we get our cubed root. The cubed root for me is over my square root button, 81 over 8, and we end up with a decimal answer. Now, this is definitely not what we want, but it is our answer, and you'll get some of your marks for it. What we need to do, so if you haven't done indices yet, where you're at is fine. That's perfect. You've done as much as you can do. If you have done indices, we need to be able to do a bit more. So I'm going to go back to this line here, and I'm going to use my rules of indices to work with that. So here are my rules of indices, and let's work with this or to get it into this form here. So here are our rules of indices from page 22, and we want to change our or that we currently have as the cubed root of 81 over 8 into something that looks like this. So the first thing we're going to do is get rid of that cubed root. So we're going to use this law here. Let me grab my pen. This law here. So we have the cubed root. So the q is a 3. Which means that this is going to be 81 over 8 all to the power of 1/3. Now the next thing we're going to do is we're going to use our bottom law here, which says if you have a fraction to a power, you can apply that power to the top line and to the bottom line. So 81 to the power of 1/3 over 8 to the power of 1/3. Now, given that we have numbers here, I will be suggesting you check them and see will any of them simplify. So if you want to check 81 to the power of 1/3, do we get a nice answer? And the answer is no. But what about 8 to the power of 1/3? And remember, power of 1/3 is the cubed root. So do we have a cubed root of 8? And the answer is yes. So this piece here, if you put that into your calculator, you'll be able to get 2. So although you're looking at this going, why can't I use my calculator? Well, the calculator won't always give us the right answer, but it can be a great help. So I have 81 to the power of 1/3 all over 2. So my B is 2. So now just to limit what we're working with, let's just take this top line here, which is 81 to the power of 1/3. Now, I want to break this into two different bases. So two bases that are the same. So I want this in the form a cubed root of a. Now, this can be a nice way to work if you're kind of stuck as to how will I work here, how do I go through this. We're able to make a little equation and then let the powers equal when we get the bases to look similar. So one way you could do this is to break the right hand side as a to the power of 1 and a to a power of a third. So this is going to be a, using law 1 here, 1 plus a third, which is 4 over 3. So you can then say, well, I have on the right hand side a to the power of 4 over 3. Here I have 81 to the power of 1 over 3. The 3 is correct, so they both have a 3 on the bottom. The top has a 4 here on the right, and this top is a 1. So could I break this 81 into something to the power of 4? So this is a little bit of trial and error. So what divides into 81? So 3 will divide into it. So if we try, it's definitely not 3 to the power of 1, 3 to the power of 2. It could be 3 to the power of 3. So if you want to try 3 to the power of 3, that's 27. 3 to the power of 4. So 81 is actually 3 to the power of 4, and that's all to the power of a third. And that is a to the power of 4 over 3. I'm going to use law 3 now on the left hand side, which says if I have a base to a power, I can multiply those powers. So that's 3 to the power of 4 over 3, and that is a to the power of 4 over 3. So that gives me my base. So I now can go back and say, well, or can be written as 3 cubed root of 3 all over 2. And if you want to now double check that, put that into your calculator exactly as we've written it, and we should get the exact same answer that we had before, which was or is equal to 2.16337 ... and so on. Now let's look at the Junior Cycle Higher Level 2022 question, and it tells us that a balloon pump is made from a cylinder with internal diameter 6 centimeters. So as soon as we see this, hopefully we're thinking, we'll need our radius. Our radius is 3 centimeters and a height of 20 centimeters as shown. Each time the pump is pumped, it passes one full cylinder of air into a balloon. Show that the volume of one full cylinder of air is 180 pi. So let's work with the volume of a cylinder. So the formula is pi or squared h. Let's sub in. So we're leaving it in terms of pi. My radius is 3, that's squared, times my height, which is 20. So I end up with 180 pi centimeters cubed, just like they asked. Part B, Dara is inflating a balloon in the shape of a sphere. When fully inflated, the balloon has a radius of 15 centimeters. Find the volume of Dara's balloon when it's fully inflated. Okay, very straightforward as well. This time we're working with a sphere. So the volume of a sphere is 4 over 3 pi or cubed. Let's fill in what we know. 4 over 3, they want the answer in terms of pi, so let's leave pi there. Our radius in this case is 15, and that's cubed. And when you put that into your calculator, you get 4,500 pi, and that's centimeters cubed. So two very straightforward parts. And the next part is that Dara pumps the pump once every second. How many seconds will it take Dara to fully inflate the balloon? So remember that each pump will put 180 pi worth of air into the balloon. The balloon's volume is 4,500 pi. So what we're going to do is we're going to take our 4,500 pi and see how many 180 pi's exist in that. So we're going to divide it in. This will tell me how many times we will need to pump the balloon, and if he pumps once every second, it will also give us the time in seconds. And that gives us 25 seconds. So far, so straightforward. We're now on part C. So Gustav is inflating a bigger balloon in the sphere, in the shape of a sphere. He also pumps the pump once every second, and his balloon is fully inflated after 50 seconds. Find the radius of Gustav's balloon when it's fully inflated. Okay, so the first thing we need to do is work out the volume of the balloon. So the volume is going to be 50 seconds worth of pumps. So that is 50 multiplied by 180 pi. Now, if you looked at this and said, oh, well, actually, since it took in the last part 25 seconds to inflate it, then this balloon must be twice the volume of the previous one. The previous one was 4,500 pi centimeters cubed, and this one is double that, so that is 9,000 pi centimeters cubed. So if you want to work in a different way to get that 9,000, that's absolutely perfect. There are a few ways to do it. The real question happens now, and it's working backwards to get the radius. And working with the sphere formula is one of the more challenging ones because it has a fraction and it also has that power of 3. So what we do is we set this up as 9,000 pi is equal to 4 over 3 pi r cubed. First thing I'm going to do, divide both sides by pi. Makes my life just that little bit easier. I also don't like my fraction, so let's get rid of that fraction. Oh, the pi is gone, sorry. So let's multiply both sides by 3. That gets rid of the 3 on the bottom there. So that gives us 27000 is equal to 4r cubed. I'm going to flip this around because I prefer my letter on the left. Always divide by our coefficient first. So let's divide that by 4. So 27,000 divided by 4. That gives us r cubed is equal to 6,750. And what we're going to do here is the cubed root of that number. We want to give our answer correct to one decimal place. We are getting this number here, which gives us, after one decimal place, the next number is 9, which means we're going to round it up. So the radius is going to be 18.9 centimeters, and that's our final answer. So that was quite tricky, and working backwards is always tricky, but it's even more tricky because we have, we were working with the sphere. But also because we weren't given the volume explicitly, we had to actually work it out. So quite a challenging question there.